Hi students, let's continue our discussion of electrostatics in the fast track revision series for JEE. In this video, we are going to start our discussion about the electric potential. Now, it is another method to represent the strength of the electric field. One we have seen it is the electric field intensity, and that was the vector quantity. Now we are seeing the second point, second way to express the electric field, that is the electric potential. What is the electric potential that we are going to see here? Now, from the very basic definition, electric potential is defined only for between 2 points, potential difference between 2 points. So from the basic definition, we say potential difference between 2 points A and B. Say 2 points are there, A and B, and we have the potential at VA is VA and potential at B is VB. Then this potential difference between these 2 points, VB minus VA, potential difference between the points A and B, VB minus VA, will be defined as the VB minus VA will be defined as the negative of the work done. If we bring some charge Q0, we bring the charge, some positive test charge Q0, we bring it from here to here, A to B. We are taking the charge Q0 from A to B. In doing so, we are doing some work. Electric force is doing some work. Negative of the work done by the electric force in bringing unit positive test charge. Q0 is positive test charge. We are taking Q0 from A to B. While doing so, electric force is doing some work. Negative of work done by that force divided by the magnitude of Q0. That will be the potential difference between the 2 points A and B. So we can write here it is equal to, we can say here it is equal to VB minus VA. Right? So from the basic definition, we cannot define the potential at point A or at point B. We can only define the potential at potential difference between 2 points A and B. It is a scalar physical quantity. Its SI unit is volt or joule per coulomb. And if you see here, a very important point is written. Please pay attention to it. From basic definition, only the potential difference between 2 points can be defined. If you want to define the absolute potential, the potential at one point, then we have to consider one reference point. Then we'll choose one point as the reference point. Say for example, you choose, if you want to define what is the potential at point A, or you want to define what is the potential at B, then you have to choose one point as the reference point. Say this point is the reference point, and at this point you will assume the potential to be 0. Then with respect to this potential, with respect to this point, you can define the potential at one point, either A or B or any other point. So to define the absolute potential at any point, it is not the potential difference, it is potential. Potential from basic definition, only potential difference between 2 points can be defined. To define the absolute potential difference at any point, we have to consider one reference point where we assume the potential of that point to be 0, and with respect to this reference point, we are going to find the potential at any point. Now another point you note down, there is no restriction in choosing the absolute reference point. I am writing here, there is no restriction in choosing reference point. You can consider any point as the reference point. There will be only one restriction. It will come in the current electricity, and in this chapter also at some places. If in the question any point is mentioned that this point is grounded, then you cannot take any other point as the zero potential, because we choose the ground as the zero potential, right? So if you want to define the absolute potential at a point, we have to take one reference point. It is very much similar to like we have seen in the work energy power chapters, etc. Potential energy, whenever we are defining, there we define the potential energy with respect to some reference configuration. Same way here, the potential is defined as the with respect to some reference point. So if I say, if among these 2 points, A is the reference point, A is the reference point, then absolute potential at point B can be defined as, the potential at point B is defined as the negative of work done by taking the charge in taking the unit positive test charge from reference point to desired point. So we can define in this way, and it is written the expression here. It is with respect to the reference configuration, the reference point. Now, many places you will see that the potential is written in terms of the external work done by external charge also. So if, say for example, actually what is happening, if we have the two locations A and B, and here some charge distribution is there, say here some charges are there, some charges, anything it can be there. If we are taking the charge Q naught from here to here, then it won't go all by itself. If it is opposite nature, maybe go. If this charge is attracting this, then maybe it will go. But if they are opposite, then same nature, then it won't go. Then we have to take it. And in the first case also, if we are taking it from here to here, work done by electric force is there something. So in short, I want to say here we need some external agent to transfer the charge from here to here, to move the charge from here to here against the electric field of this, right? Or in the direction of electric field also. Remember this, slowly it will be very clear to you. Now, if we are taking this charge, the charge from A to B against or in favor of this electric field, the electric field created by this charge distribution, which I have encircled by red color. So due to this charge distribution, some electric field is here and we are moving in this electric field, then some external agent has to perform some work to move from here to here. Some external agent has to perform the work to move from here to here. Now, from work energy theorem, we can write change in kinetic energy is equal to work done by electric force plus work done by external force. Now, in the potential definition, we have the work done by electric force. If we want to write the work done by in terms of work done by the external force, then we have to move the charge slowly. If charge moves slowly, then delta Q becomes 0. And then what we can say, if charge Q naught is moved slowly from A to B, then from the work energy theorem, we can say change in kinetic energy equal to 0 because the charge is moved slowly, and this is equal to work done by external plus work done by electrical. So work done by electrical force comes out to be negative of work done by external force. So then the potential definition, in the potential definition, what we can write, VB dV, what we have written V8 VB equal to negative of the work done by electric force. So in place of this, we can replace it by work done by external force. But you remember, when you are saying in terms of work done by external force, there the charge particle, the system is moving slowly. If the system is moving with some kinetic energy, some change in kinetic energy, then this concept is not going to be applicable. This concept is applicable only when system is moved slowly, if the charge is moved slowly. And we can write the expression in this way, the potential difference between 2 points A and B is equal to the work done by external force in taking the charge particle from A to B per unit positive test charge, or potential at a point from reference to the desired point, work done by external force. If you are writing in terms of the electrical force, minus sign will come. If you are writing with respect to the in terms of external force, then minus sign won't come. And remember, this is valid only if charge is moved slowly. If the charge is moved with some change in kinetic energy, then you cannot write the potential in terms of work done by the external force, because in that case work done by external force is compensated in two places. One, work done against the electric force, and second, it is changing the kinetic energy. Potential energy is defined only corresponding to the conservative force, only corresponding to the electrical force. What is the work done against that? Only for that part it is there. Now, if I say few points, you see, potential difference between 2 points. If we are saying there are 2 points A and B, potential difference between these 2 points VA minus VB, whether you take this C as the reference configuration or D as the reference configuration, when C is the reference configuration or D is the reference configuration, it doesn't matter. Potential difference between 2 points will remain same. But potential at one point depends upon the choice of reference configuration. If you choose point B as the reference configuration, potential at A may be V1. If you choose C as the reference configuration, potential at A may be V2. When you choose D as the reference configuration, potential at A may be V3. And these three are going to be different. While VA minus VB, whether you choose C or D as the reference configuration, is not going to change. It means the potential difference between 2 points is independent of the choice of reference, while potential at a point depends on the reference configuration, choice of reference point. Right? Remember, it is a scalar physical quantity. It is not a vector physical quantity. And with the help of some examples, we are going to see that part also. Now, take the next thing, next heading, relation between the electric field and electric potential. Now, we are saying electric field and electric potential are the two ways to represent the strength of the electric field. Is there any relation between these two, electric field and potential? That's what we are seeing. Let us consider there are 2 points A and B in an electric field region. There are 2 points A and B in an electric field region, and the separation between these 2 points is dr vector. And in this region, the electric field is E. In this region, electric field is E, and the potential difference between these 2 points A and B is dV. Potential difference between these 2 points is dV. Then from the very basic definition, what we have just seen for the potential difference between 2 points is negative of the work done by electric force in taking the charge, unit positive charge, from A to B. So dV is equal to negative of the dWEL. Now, work done by electric force can be written as electric force dot dr. That what is the Q naught charge? Then E is the electric field. The force is Q naught E into dr divided by Q naught. Q naught cancel. So what the expression we have? dV equal to minus E dot dr. dV equal to minus E dot dr. This is the expression for the expression which is relating the potential and the electric field. If you integrate this between the 2 points A and B, VA to VB, At RA, velocity is V, potential is VA. At position vector RB, it is VB. And this can also be written as V equal to, if A is at the reference point, if I say A is at the reference point, and generally what happens, reference we take at infinity, that's why here I have written as infinity. So potential at a point can be defined as the negative of the E dot dr if we go from infinity to the desired point, right? So this is the relation between potential and the electric field. Now here I want to say something more. What is this negative sign is telling? This negative sign is telling us, negative sign tells that electric field points from higher potential to lower potential. Where the electric potential is higher, from that point to lower potential point, direction of electric field will be there. I'll explain this point also. Let us say there are 2 points, A and B, and potential of A is more than the potential at B. Then you can say direction of electric field will be this one. Direction of electric field will be from point A to point B, provided VA is greater than VB. Electric field points from higher potential to lower potential. Now here we have written V in terms of E. We can also write E in terms of V, and we have the expression here. This is what E equal to minus dV by dr. If V is a function of R only, and if V is a function of x, y, z, then we can write it as minus dou V by dou x I cap plus dou V by dou y j cap plus dou V upon dou z k cap. So negative of this encircled term, right? This is going to be the relation between the field E in terms of V. Now this is already I told, E points from higher potential to lower potential. Now here you take one particular point. If say for example someone is saying electric potential changes linearly, say from 10 to 40 over a distance of say 30 centimeter, and this is volt, 10 volt to 40 volt over a distance of 30 centimeter along this direction. What is the value of electric field? Then by using this expression E equal to minus dV by dr, first thing, electric field points from higher potential to lower potential. So the direction of electric field will be in this direction. It is not in this direction. It will be electric field points from higher potential to lower potential. And what will be the value? E is equal to dV by dr. So dV is 30 and dr is 30 centimeter. So it is 1 volt per centimeter. Electric field is 1 volt per centimeter. But here you have to remember a very important point coming. Here we have used E equal to dV by dr minus dV by dr only along one direction. So this is giving us the component of electric field in this direction only. Component of electric field along this x-axis. Here no information about the y and z axis given, so there we can't say what is the electric field, but we can say with surety that electric field along the x-axis is going to be 1 volt per centimeter towards the negative x-axis. So it is a very important point. So here I'll like to summarize in 1 minute. If we have the potential V in a region and E is electric field at that particular point, then potential difference between any 2 points will be related as the electric field intensity as dV equal to minus E dot dr. And by using this particular relation and integrating this expression, we can find out the potential at any one point or the potential difference between any 2 points also. And then we have the same expression if we have to find E in terms of V. If V is given and E we have to find, then we can use E equal to minus dV by dr along the r vector, or we can find the, if V is given as a function of x, y, z, then E can be found as E equal to minus dou y by dou x I cap minus dou v by dou y j cap minus dou v by dou z k cap, where dou v by dou x is the potential derivative of V with respect to x only, treating y and z will be constant. Right? Let's move to the next part. Now, potential we are discussing. Remember, potential is a scalar physical quantity. So just like in the electric field, we have seen the electric field due to the point charge, due to the system of point charges, due to the continuous charge distribution. Same way, we are going to find the electric potential due to a point charge, due to a system of point charges, and due to continuous charge system. Again, remember, whenever potential you are writing potential expression, charge has to be substituted with sign. It is not a vector quantity. It is not a vector quantity, but still in potential you have to write the sign. If the charge is positive, write the charge in the expression what we are going to see. In that expression, charge you have to substitute with sign. If negative charge, minus with minus sign. If positive charge, with positive sign. So first of all, we are taking the electric potential due to a point charge and system of point charges. So if we have a point charge Q here, if we have a point charge Q here, and we are interested in finding the field here at point P. At point P, we are interested in finding the field which is at a distance r from the point charge Q. So formula is V equal to V at this point, V at point P due to Q will be Q upon 4 pi epsilon naught R, or we can also write it as KQ by R. Right? There is no direction associated. Now, if electric field we have to find, electric field will be in this direction if positive, in this direction if negative. But here, nothing like that will come. It is very simple as compared to the electric field. Here, only the potential, direct you write KQ by R. Now, principle of superposition is valid here also due to a system of point charges. We are having some charges, say Q1, Q2, Q3, Q4, Qn charges are there, and they are at a distance of R1, R2, R3, Rn from this point P. Then the total potential at this point P will be given by sum of the individual potentials. Sum of the potential at point P due to the individual charges. So due to Q1, due to Q2, due to Q3 and so on. So the potential at point P due to Q1 is KQ1 by R1, due to Q2 is KQ2 by R2, due to Q3 is KQ3 by R3, and due to Qn is KQn upon Rn. Potential at point P due to nth charge is KQn by Rn. So the total potential comes out to be K common summation Qi by Ri. This will become the potential. Let's take one question. I'd like to take one question here. If we have a point charge here, say 4 point charges we are taking at the vertices of a square, 4 point charges, say Q, 3Q, minus 2Q, and Q. And we are asking the potential at this point at the center, and this you directly say this particular distance is A. The distance from the vertex to the center is A. Then what is the potential here? Due to this charge, it is KQ by A. Due to this charge 3Q, potential here is K into 3Q by A. Due to this minus 2Q charge, it will be K into minus 2Q by A. Due to this charge, it will be KQ by A. So the total potential comes out to be K by A Q plus 3Q minus 2Q plus Q, and it will become 3KQ by A. So electric potential due to point charge system is very easy to determine as compared to the electric field you have to find. In electric field, you have to take care of the direction. Remember this point, electric field is a vector quantity, potential is a scalar quantity. Here you can ignore, not ignore, here no need of direction, while in the electric field direction plays a very important role. Let's move to the next part, electric potential due to continuous system of charges. There in the continuous system of charges in the electric field, we have taken the ring, we have taken the disk, we have taken the infinite charge, long wire, infinite long sheet, finite length wire, and all such things we have seen there. Here also we are going to consider all the common system, common object. The first one is uniformly charged circular ring. Uniformly charged circular ring means we are having one ring, charge on this will be distributed uniformly. What is the potential at the center and at the axial point? Now here if you see, the charge Q is distributed here. So potential at the center is Q upon 4 pi epsilon naught R, because the total charge is at the same distance R from the center. Same way at the axial point, electric potential due to this charged ring at axial point will be KQ. K is 1 upon 4 pi epsilon naught Q upon 4 pi epsilon naught under root R square plus X square. This is R and this distance is R square plus X square. So at the center it is KQ by R. At the axial point, KQ upon under root R square plus X square. Electric field at the center was 0, and at the axial point it was KQX upon R square plus X square to the power 3 by 2. So formulas you have to remember. And one very interesting fact, this you note down. Now the formula for the electric field and this potential are there, which we have said uniform charge distribution. Now if I say, if this charge Q is not distributed uniformly, rather the amount of charge remains same, but it has been distributed non-uniformly, means this total charge Q may be here only. This total charge Q may be Q by 2 here, Q by 2 here, or it may be Q by 2 here, Q by 2 here, or it may be Q by 3 here, Q by 2 here, Q by 6 here, and something here, in this way at different points. In all cases, potential at this point, potential at the center will be same. Potential at the center will be same. But electric field is not going to be 0 only. So what I want to say, the above formulas are applicable even if charge is distributed non-uniformly. But this won't be the case with electric field. This is electric potential due to the continuous charge, uniformly charged ring at the center KQ by R, at the axial point KQ upon under root R square plus X square. Then we have the uniformly charged disk. Due to the charged disk, electric field at the center, potential at the center is Q upon 2 pi epsilon naught R, Q upon 2 pi epsilon naught R, and at the axial point is Q upon 2 pi epsilon naught R under root X square plus R square minus X by R. Or you can also write the next object, potential due to infinite long line charge. Now the very important point you remember, Due to infinite charge distribution, we cannot define the potential, because at infinity we have taken the potential as to be a reference point. So due to infinity, at another infinity, this type of things are not going to work. So potential due to infinite charge objects are not defined. But for these objects, we define the potential difference. Then due to infinite long charge, what is the potential difference between 2 points 1 and 2? Then electric field points, if this is positively charged wire, electric field will be in this direction. So electric field points from higher potential to lower potential. So V1 is going to be more. So you can write V1 minus V2 equal to lambda upon 2 pi epsilon naught ln R2 by R1, or V2 minus V1 equal to lambda upon 2 pi epsilon naught ln R2 by R1. This is the expression for the potential difference between 2 points due to infinite line charge. Due to infinite plane sheet of charge, it will be dV equal to minus E dot dr. E is constant. E is constant. So E is sigma upon 2 epsilon naught into R2 minus R1. That comes. R2 minus R1 means that is going to be electric field is in this direction. This is positive. This is higher. This is lower. So electric field points from higher potential to lower potential. Now, this you remember, electric potential due to infinite lengthy objects we cannot write. We write only the potential difference between the 2 points. Let's take the another object, electric potential due to uniformly charged hollow sphere. Hollow sphere already we have told. Due to the hollow sphere, electric potential at any inside point will be constant, and at outside point it will be same like a point charge placed at the center. Electric potential at any inside point is equal to kq by r, means the potential here is k into q by r, q upon 4 pi epsilon naught, and at any outside point is kq by r, that is q upon 4 pi epsilon naught r, which is same as that of the point charge placed at a distance r. So for any outside point, the uniformly distributed hollow sphere can be considered as a point charge placed at its respective center. And here if you see, it is the graph. For small r less than capital R, it is constant, and then it is having the inverse relation. Then we have the due to the uniformly charged solid sphere, very much similar concept like the in the field, but here formulas are slightly different. For inside point, the potential is given by this expression, kq into capital 3r square minus small r square upon 2r cube, where small r is the distance from the center where we are finding the potential. So potential at this point is q upon 4 pi epsilon naught into 3 into this capital R square minus small r square upon 2 into capital R whole cube. This is the expression. If you want to find the potential at the center, you substitute in this expression r equal to 0. If you substitute r equal to 0, you are going to get 3 by 2 kq by r, means 3 by 2 times of the potential at the surface. The graph is going to be like this one. This is a corresponding to this equation, and this is corresponding to this equation. For outside point, it is just like the point charge placed at the respective center, right? That's all for now. Remaining will continue in the next video.